In this video, let us calculate the wavelength of hydrogen spectrum using Hartmann interpolation formula. In this experiment, we will use mercury spectrum to standardize the prism. First, the telescopic readings for the prominent lines of mercury spectrum is noted. For red, the telescopic reading is 28.8, and for the green, the mean color, it is 30.3, and violet, it is 34.3. And these three readings are taken as D1, D2, and D3, and the corresponding standard wavelength for red 6234 is taken as lambda 1, and for green it is 5461, it is taken as lambda 2, and the extreme in violet 4044 angstrom, this is taken as lambda 3. So these are the formula which will help us to find the wavelength of hydrogen spectrum. There are a set of formulas which are used to find out the Hartmann's constant. Using this Hartmann's constant, we will find out the wavelength for the hydrogen lines. The first Hartmann's constant is x, which is given by lambda 1 minus lambda 2 into d3 minus d2 divided by lambda 1 minus lambda 3 into d2 minus d1. The next constant is d0, d1 x minus d3 divided by x minus 1 meter. And next we have c, which is given by lambda 1 minus lambda 2 into d0 minus d1 into d0 minus d2, the whole divided by d1 minus d2 meter square. The next we need to find out lambda naught, which is equal to lambda 1 minus c divided by d0 minus d1 meter. So using this constants, lambda naught, c, d0, we can find out the spectral lines of the hydrogen spectrum using the formula lambda h equal to lambda naught plus c divided by d naught minus dh meter. Here we are going to find out h alpha, h beta and h gamma lines of the hydrogen spectrum's wavelength. So first let us find the constants. First let us find x. So x is given by the formula lambda 1 minus lambda 2 into d3 minus d2 divided by lambda 2 minus lambda 3 into d2 minus d1. So this d1, d2, d3, lambda 1, lambda 2, lambda 3 corresponds to the mercury spectrum. See, all the constants are found using mercury spectrum values. So substituting those values in x, we get 6234 into 10 power minus 10. But while doing calculation, it is always important to express the parameters in terms of MKA system, that is meter, kilogram and seconds. So here also I have converted angstroms into meter. So 1 angstrom is 10 power minus 10 meter. So substituting the values, we get 6234 into 10 power minus 10 minus 5461 into 10 power minus 10 into the values of d3 minus d2 is 34.3 into 10 power minus 2 minus 30.3 into 10 power minus 2. The whole is divided by the lambda 2 is 5461 into 10 power minus 10 minus 4044 into 10 power minus 10 into 30.3 into 10 power minus 2 minus 28.8 into 10 power minus 2. See, in the numerator, in lambda 1 and lambda 2 we have 10 power minus 10 in common, we are pulling it outside, and in the next term d3 minus d2 also we have 10 power minus 2 common, so we are pulling it outside. In the same way, in the denominator also we have a 10 power minus 10 and 10 power minus 2 in common, we are pulling it outside. So we are left with 6234 minus 5461 into 10 power minus 10 into 34.3 minus 30.3 into 10 power minus 2. The whole divided by 5461 minus 4044 into 10 power minus 10 into 30.3 minus 28.8. So all the powers in the numerator and the denominator will get cancelled out each other, and Finding the difference of values, we get 773 into 4 divided by 1417 into 1.5. So multiplying, we get 3092 divided by 2125.5, and x leads to dividing the numerator and the denominator. We get x equal to 1.458. Please do not check your answers with the your next batch, because the x is a constant which will vary from one set of readings to another set of reading. It is not a it will not be the same for all. So we have found x. Next, we are going to find out what is c. Next, we need to find out what is d naught. D naught equal to d1 of x minus d3 divided by x minus 1 meter. So the value of d1 is 28.8 and d3 is 34.3 into 10 power minus 2 meters. So substituting the values of d1, d3 and x, look at the first term. d1 of x 28.8 into 10 power minus 2 into 1.458 minus 34.3 into 10 power minus 2. So in the numerator, in the first term and second term, we have 10 power minus 2 in common. Multiplying the first term, we get 41.990 into 10 power minus 2 minus 34.3 into 10 power minus 2. So we can pull out the 10 power minus 2, and in the denominator it is 0.458. So the difference of these two reading 41.9904 minus 34.3 will give you 7.6904 into 10 power minus 2, the whole thing divided by 0.458. So when you divide the numerator by the denominator, we get d naught value as 16.791 into 10 power minus 2 meter. Again, this d naught will also be not same for all. Each of you will get different readings. So different for the different set of d1, d2, d3 readings, you will get different d naught. Please do not compare your answers with the next batch students. So next we have to find out what is c. The formula to find out c is lambda 1 minus lambda 2 into d naught minus d1 into d naught minus d2, the whole divided by d1 and d2. Substitute all the values of lambda 1, lambda 2, d naught, d1 and d2. So when you substitute, we get 6234 into 10 power minus 10 minus 5461 into 10 power minus 10. See, in this 10 power minus 10 is common in lambda 1 and lambda 2. We can pull out this 10 power minus 10, and difference of these two will give us 773, which is next written in the next step. Then d2, d naught minus d1, you could see 16.791 into 10 power minus 2 minus 28.8 into 10 power minus 2. So here the 10 power minus 2 is common, which is taken outside for both the terms, and the difference of these two will give you minus 12.009. So okay, the next term is d naught minus d2, that is 16.791 into 10 power minus 2 minus 30.3 into 10 power minus 2. So 10 power minus 2 is common, you can take it outside. So within the brackets you have minus 13.509. And in the denominator we have d1 minus d2, which is equal to 28.8 into 10 power minus 2 minus 30.3 into 10 power minus 2. Again we have 10 power minus 2, 10 power minus 2 common, we can take it outside. See, in the numerator we have 773 into 10 power minus 7 minus 12.009 into 10 power minus 2 into minus 13.509 into 10 power minus 2. The whole divided by minus 1.5 into 10 power minus 2. So 1 10 power minus 2 in the numerator and the denominator will get cancelled. The remaining powers will be 10 power minus 12. So multiply everything, you get 12,403.46. The whole divided by minus 1.5. So we got the value of c as minus 83,602.3 into 10 power minus 12 meter square. Always keep the power of c in 10 power minus 12. So it will be easier for you to calculate lambda naught, lambda h and all. So do not pull the powers inside or extract it. So keep it as 10 power minus 12. So the value of C here is minus. Some of you may get positive C value, or some of you might get a negative C value. Again, this C value will not be same for all. It will be different from for your next batch of students. So next, find out lambda naught. So the lambda naught is given by lambda 1 minus C divided by D naught minus D1 meter. We know the value of lambda 1 as 6234 into 10 power minus 10 minus, so the value of C is minus 83602.3 into 10 power minus 12, the whole divided by D naught minus D1. So D naught is 16.791 into 10 power minus 2 minus 28.8 into 10 power minus 2. So you can pull out the 10 power minus 2 common in common. So you will get 6234 into 10 power minus 10 minus of minus 83602.3 into 10 power minus 12, the whole the divided by minus 12.009 into 10 power minus 2. So this 10 power minus 2 and the 10 power minus 12 there will get cancelled and will give you 10 power minus 10. The minus in the numerator and the minus in the denominator will get cancelled. So dividing this, you get 6234 into 10 power minus 7 minus 6961.63 into 10 power minus 10. The reason why I asked you to keep C in terms of 10 power minus 12 is this. So this minus 2 and minus 12 will get cancelled and will give you 10 power minus 10. So the lambda 1 and this factor will have the same powers, 10 power minus 10. So since they have a 10 power minus 10 as a common value, the difference of this will give us lambda naught equal to minus 727.63 into 10 power minus 10 meter. So we have found lambda naught. So we have found all the constants of Hartmann's constants. Next, look at the values of hydrogen spectrum. So these are the experimental readings taken for hydrogen spectrum. For the red line, that is H alpha, the telescopic reading is or the scale reading is 28.2, which we are going to take it as D1 henceforth. And then for bluish green color, which is generally called as H beta, it is 31.8, it is taken as D2. And the blue color H gamma line, it is 33.4, which is taken as D3 here. Or in general you can call it as DH. Instead of calling it as D1, D2, D3, in general term you can call it as DH. Okay, now let us calculate what is the H alpha line. So H alpha line corresponds to red color. So DH here is 28.2 into 10 power minus 2 meter, and the lambda H is equal to lambda naught plus C divided by D naught minus DH meters. So we know the value of lambda naught is minus 727.63 into 10 power minus 10 plus the value of C is minus 83602.3 into 10 power minus 12. That is divided by 16.791 into 10 power minus 2, that is D naught, minus the reading corresponding to red color is 28.2 into 10 power minus 2. See, in the next step, we have subtracted 16.791 and 28.2, and 10 power minus 2, which is common in both the terms, is taken out. So this 10 power minus 2 and the 10 power minus 12 in the numerator get cancelled and will give you 10 power minus 10. And dividing 83602.3 by 11.409 gives us 7327.75 into 10 power minus 10. So look at the values of lambda naught and the second term. So both have the common powers 10 power minus 10. Subtracting minus 727.63 plus 7327.75 gives us 6600.12 into 10 power minus 10 meter, or the H alpha value is 6600 angstrom. Next, let us find out the H beta value, that is for bluish green. For bluish green color, the scale readings is DH is equal to 31.8 into 10 power minus 2 meters. Substituting, we get lambda H is equal to minus 727.63 into 10 power minus 10 plus the C value minus 83,602.3 into 10 power minus 12 The whole divided by 16.791 into 10 power minus 2 minus 31.8 into 10 power minus 2. So upon simplifying, we get the H beta line as 4842.51 into 10 power minus 10 meter or 4842 angstrom. In the same way, we can find it for blue color also. So here the results has been tabulated. So we have found the wavelength of the spectral lines of the hydrogen spectrum using mercury as the standard or reference wavelength. See, the calculated values are observed wavelength for red, that is for the H alpha spectral lines of hydrogen spectrum, is 6600 values, 600 angstrom, which is against the standard wavelength of 6562. So there is a difference of some 40 angstrom. Let's not bother much into it. There may be some difference of 200 to 400 angstrom is permissible. For the bluish green, the obtained calculated value is 4842 angstrom, and the standard value is 4841 angstrom, and for the blue it is 4306 as a calculated value, and the reference value is 4340 angstrom. So the calculation we have done for the hydrogen spectral lines are all in accordance with the standard lines or standard wavelength of the spectral lines of hydrogen spectrum.